So welcome to 4377. You may remember me talking about how SMTP servers, which are the servers that accept email from your email program and then will send it to another SMTP server, whichever one is designated for that other domain. So let me just remind you, we'll just pull up MX Toolbox, and what I'll do is look up uh.edu, and you notice I have the MX lookup tool that was pulled up here. So what it's going to do is try and pull the MX records from DNS, and here they are. So there's way too many, which is part of the reason why I think we lose control of them and systems get hacked and we're not applying. You know, how can you manage 20 systems? Why do you need 20 email servers? You know, we need one. Anyway, off topic already, but these are the servers where you will be directed to connect your client, and all of your email interaction will be with that one server, at least as far as U of H's domain is concerned. And when it's time for you to send something to someone from your U of H email account, the receiving SMTP server, which your sending server can identify by pulling these very records you're looking at here. So if I wanted to send something to rice.edu, then I could look them up as well. So let me pull up a second window and do that, and we're going to get rice in here. And I'll be able to get both of these things going at the same time. I really need this window to go away. It's like completely in my face. How the hell do I get it to disappear? Okay. So here's Rice's on the right, and U of H is on the left. So when I try to send something to Rice, U of H will look up this address, open a connection to it. Rice will then do a reverse DNS lookup and figure out, it's not exactly a reverse, but they'll do one in the opposite direction of the protocol to make sure it's coming from a server that really is representing U of H.edu, and then and only then will accept the email. Well, that makes it impossible for you and me to try and connect to an SMTP server and send it SMTP commands, because they usually will not accept them from us because they have too many security restrictions. So there are a couple of ways of solving the problem. We played around a little bit with one that I was stunned to find was still open at CS. It shouldn't be, but it wasn't last time I looked a year ago, but someone's opened it back up again. So that's one thing. That's in the slide. That's not in the textbook. Another one is, let me see if I can find one here, SMTP test server. You can Google for something like that, and you can find one, Mailtrap.io, fake SMTP testing server, dummy SMTP email testing. Here's a MX Toolbox. They've got something. Wormly's got one, and then SendGrid is one. There's some really nice ones out there that will let you test sending 10,000 things at once or receiving hundreds of things at once, et cetera. So this market has mushroomed or blossomed, I guess, because of, I guess I need to pick fungus or flower to make my decision of blossomed or mushroomed. It's come up because people don't have any other way of testing things. So if you're writing an email client, you know, how are you going to test something without spamming everybody? That's kind of the problem. So I found one that I want us to try using that I think will be, you know, lots of fun for us, and it's called Mailcatcher. So I'm going to pull up the homework that we've got and walk us through a little bit of it. You do not have this homework yet. So I categorize this as an experimental problem. If you can't get it to work in an hour, let me know as much as you can about what went wrong, include screen dumps. You need to try to get it to work. You can't just try the first command and then, you know, nothing happens after that. And you'll get credit for the problem that way too. So try, right? That's the goal of education, right? We want you guys to learn what's going on. So Mailcatcher is a program. You can install it by, like you can some other public domain software with other install command tools. But Jim is a tool that already knows where to go on the internet to look for a program. So people will register their programs, and then anyone in the world, they don't need to know the URL, they don't need to know how to log in. All they use is one of these installation packages like Jim, And in this case of Gem, I tell it to install, and I say what, and so it will go out and find Gem repositories where people have registered where to go to find Mailcatcher. And so that's how you get it installed. So it works differently on different systems, and it's possible. It looked like Gem was already installed on my Mac when I did this for the first time last summer, but it's possible that it's just already there because I installed it previously and just forgot. But I give you the Windows command as well. There's also a website here you can go to that will kind of walk you through how to get things done. And they've got some cool stuff in here, but they basically walk you through how to get it installed. Meanwhile, back at the ranch, what I did was once I installed it, I ran it. And so when you run it, it's a server. What you're basically installing is an SMTP server. And it's different than some other Unix commands because when it runs for a second or two, it gives you back your command prompt. And you might think, okay, well, that's it. It's finished. But it isn't. It runs as a daemon. And so what that means in Unix is it starts up in the background. And I'm getting some sun glare here. Let me see if I can fix that for you guys. So it is still running, and it's been running since yesterday. They give me a couple of nice little helpful URLs. One of them is for the web front end that they give us. So this web server has a SMTP server has a little web front end so I can monitor what's going on. This is how you learn how it's working. And then it also has an SMTP URL, which, believe it or not, you can type into a browser because your browser speaks lots of different languages. It knows how to speak Java. It knows how to speak HTTP and interpret HTML. It knows how to open spreadsheets and Word docs and PDF files. It knows how to play MP4s and MP3s. So it's actually a potpourri of tons of client applications all built into the hood of something we call a browser. And one of the things it does is email as well. So you can actually go to a browser window and say something like mail to //kblong@uh.edu, and it's not going to completely run in the browser because my Mac has been configured to pull up a mail program, but it will interact. It responds to lots of different URL uniform identifiers than just HTTP. So if you've never played with it, you can also get to FTP places like this won't work, but you can at least see that it's going to try to open one. So lots of different communication protocols here. All right, one of them is SMTP. So if I go to this URL for HTTP, it pulls up this web page. And in the beginning, there's nothing here. So here comes the second command prompt, this one in the background. And what I'm going to do for this is refer to the script in the book, but I've also pasted it into the email, into the homework. And it basically looks like this in the 7th edition of the book. In the 6th edition, this beginning of this script and the end are all on one page. But this is the script. So this is valid SMTP commands, and this is kind of what I want you to follow, except I don't want you to do exactly what they do here. So let me just try and do this. So what I'm going to do is telnet to the IP address of myself. And without needing to know my IP address, you can always telnet to what's called a loopback address, 127.0.0.1, and that is always you. It's always you. So you can Wireshark that address as well. In fact, if you pull up Wireshark, one of the interfaces that you'll see that you may not have paid much attention to before is your loopback. So when you're looking at where there's activity, one of them where there's always activity is the loopback account. So I'm going to start that up, and we're going to start grabbing packets. And this is probably the very first time you've ever seen anybody run Wireshark where there's no packets yet. There's a couple. We can take a look. Here's some more in here. LAN sync discovery protocol. So what I'm going to do is telnet to this address, which is me, and I'm going to do it at port number 1025, and I do it at port 1025 because the docs tell me to, but it's also where the SMTP server is running. Okay, you ready? I'm going to hit return, and I generated some packets over here, and I get a response from the server trying to connect. Now what I'm going to do is follow this script. I'm going to say HELO uppercase, and I'm going to say kblong@uh.edu. Make up whatever address you want. Make it yours. Make it so I can see this and know that it's you running this test. And it says, okay. And now I'm going to say mail from, because it's the next thing over here in the script. The client sends mail from. The server sends program sends various messages. Mine sent back event machine SMTP server. Okay, whatever. So mail from, and I'm going to say kblong@uh.edu. With brackets, it says OK. And I'm going to say receipt to, so this is who I'm sending it to, kblnhou@gmail.com. That's my other email address. And it says, all right, and now I'm going to send the email message. So I type in data, and happy Valentine's Day to the Tuesday. This is Thursday. I need to get on the right day. Thursday morning COSC437 class. All right. So what I want you to do is send a mail message in here that says hello from your name and your PeopleSoft ID number, so I know that it's you. If your TA asks you to, you may need to bring up a University of Houston login page as well and log in so that it shows who you are. And when you do your screen dump in a minute, just kind of have that thing sitting in the background. So it's got it right here. And now that I'm done with this email message, I can hit a period and hit return. And it finishes sending it. And then the last command, I'm not going to go back over to there again, but the last command is quit. All right, so I'm done. I've opened a Telnet window. I've followed a valid SMTP delivery script to hand an email message. This is what your user agent would actually do. Now I'm ready to go back over to my email web page. And here it is. It's over here. And I'm going to refresh this page. Now, right now, there's one in here from yesterday. So I'm going to refresh it. Now there's two. There's a new one, Thursday, February 14th. I click on source. There's the message. I bring up the two Telnet windows, and you can shrink them down. And I don't need to do Wireshark, but that's for us, for fun. I may ask you to do some things in Wireshark because it's super easy. The other thing I'm missing is this Access U of H page. So I need to kind of pull that down here and rearrange things a little bit so it's visible. And pull these two, not that one, this one. Pull these two windows back up. And now what I'm ready to do is take a screenshot of this thing. What would be nice to do is if I don't show the date and time, which it does here, I can always grab it up here and go back to the homework assignment. And what it says to do is paste your screen dump here. So that's where you paste it, and that's where your grade is going to come from. So the problem is I have no idea if this is going to work for any of you guys. I think it'll work for some. It worked for some of my summer students, but I want us to give it a shot because I need to iron this out. If it doesn't work on this one, then next semester I'll try a different mail program. So I'm going to chip away at this thing until I find one that's fun. While we're here, let's take a quick peek over at SMTP. I can't spend too much time on this because we've got a bunch of stuff to cover, but you can basically see here you have your TCP handshake that starts off, and you notice Wireshark drew me a little line here that goes all the way down to 64 to show this is basically the TCP session. So that's very helpful to know that it starts from here. I have a SYN, a SYNAC, and an ACK. That's my three-way handshake. I have a window update, which basically says I feel comfortable enough with the behavior of this network that I'm willing to send 63,860 bytes at a time, not just the default 1025. And so the other side says, yeah, okay. And you basically can renegotiate down if you need to. This one is now at 40,008. That this is basically the two sides, the server and client TCP software, negotiating on how much buffer do I have for things that you can send me without overflowing me. Because what I may do is like ship you a truck full of 10,000 pounds of sugar because the road can handle it and the truck can handle it, but can you handle it? Do you have enough room in your storage closet at the restaurant for 10,000 pounds of sugar? Maybe not. So you're constantly communicating back and forth, as well as the drivers paying attention to the road conditions. You know what? This bridge is weight restricted. We can't go over that. There's a really long backup. We need to take a different route, et cetera. So both of those things are happening. And then you finally get back down here where there's some other things that are just going on, have nothing to do with email. And then you have some SMTP messages in here where you're sending things basically back around. We can try looking a little bit of the data and see if we can find anything interesting in here. ACKs. So we'd have to dig around a little bit. And you'll notice 127 is both the sender and the receiver, which is really odd in here as well. Okay, I suppose I could stop capturing now. Anyway, that's the mail catcher, so watch for that. And we were up to streaming. We kind of plowed quickly through point to point, so I'm going to back up a few slides and kind of re-mention a couple of things that BitTorrent does. It's pretty intelligent about not letting people freeload too much. One of the things it has is a tit for tat protocol. So if you are a user and you are receiving data, then it expects you to periodically give something back, to publish your server. I'm always pretty scared to do that because it's usually stuff that I don't have copyright on, and therefore it's illegal. And how would that look in the paper? So I usually won't. It's not going to look like anything in the paper because first of all, nobody reads it, and second of all, nobody's going to put it in there. But I've told you I was paranoid about it, not logical. So that's one thing that BitTorrent will do. The other thing that it'll do is every once in a while just experiment with walking up to somebody on the playground that you don't know already and decide you're going to say hi to them, would you like to play? So I'm going to optimistically allow a connection to be made to someone that I currently don't send anything to, and it's called unchoking, which is unfortunate. So the way this basically works is I'll try Bob out. Now in this case, and in some cases in reality, it turns out to be a very wise decision because Bob has a library full of objects that I might want, and he's got really good friends and a really good connection between him and me. So for whatever reason, we're able to send lots of stuff back. So it became one of Alice's top 4 providers, found a higher upload rate. I can share stuff faster, get stuff faster. So it's constantly exploring and experimenting with the network. All right, we've talked a lot about CDNs in the past, and basically over half the traffic on the internet in the evenings is people watching movies. And we may have had a chance to just kind of briefly get into this, but this is where we're going to spend most of the rest of our time today. So when it's time to send video sequences, it turns out to be mathematically super difficult to read the papers on exactly how they do this stuff. And if I can find a PDF in here for us, there's a really good set of documents. Here's a book that's not bad on it, but the JPEG standard is just tough. One of the things that these image standards do is something called discrete cosine transformation. And it's tough to figure out. But just to kind of give you a sense of how they go through an image and they value the pixel areas in 8x8 squares and come up with a way numerically of representing how much change is in here. This has the very curious mathematical property when you apply this formula to an image of creating a matrix that almost always looks like this. A few numbers in the top left corner and nothing anywhere else. So this is extraordinarily compressible. It's one number and the rest, you can even tell the other side. If I don't tell you what they are, assume they're zeros. So instead of sending 64 objects, in this particular case, I send 1. And in general, basically what they're doing is they're taking a whole series of multiples of 16ths of cosines. So this graph shows various points along a curve that represents the first row of these cosines. And this one shows double the periodicity, and then you can see the waves are getting closer and closer together. And you can represent what's going on in an image by representing the value on each of these curves. So to give you a little bit of an example that's doable, let's say my value is really sort of right here. So I'll go ahead and select this one, but I've overshot the runway, right? I'm too far north of the value I want to represent. So I'm going to go to the next one. This one's negative. I'll pick it too. Well, I'm not at 0. I'm a little above 0. I'm closer. I definitely don't want any of this one or this one, but this one I'll take because it'll pull me back a little bit north again. And this one I probably don't want unless there's a way for me to specify only a portion of it, for example. But most of the rest of these I don't need, and therefore they're zeros. So what I did was just encode the first row, and you can apply a constant in front of it. So if you work your way through that, so I want you to stop and back up here and think a minute. Really? We're doing this for every 8x8 pixel square in a 4K image 60 times a second, and then building packets out of this and sending them to the other side and then decoding all of this? Yeah, that's exactly what you're doing. And this is only JPEG. This isn't even MPEG. So this isn't even full motion video. So you end up with this matrix of values, and you can basically send it. So it's tough math. If you're a math major taking this class with me, or had that background, and you want a special project, come talk to me, because I could use some help putting together a more discernible lecture for computer scientists based on this stuff. And I need to work with somebody who's got more math than I do. And so it's possible that it could be you. All right, so that's what's going on, but we have other ways of encoding images as well. And again, to kind of remind you, we have a budget, a certain size of packet, because in order to maintain the illusion of motion, I have to make sure I'm sending packets over time on a very regular basis. For voice, it might be every 10 milliseconds or 50 milliseconds, and for video, it may be a little less than that. So if this is the periodicity I have, and I may once in a while be able to duplicate, if a packet like this one gets dropped, I'll just repeat the one that I had before. And VHS cassettes, if you guys are old enough to remember those, like Blockbuster Video, what they actually did was they played 3 frames and then repeated the third one. Always, forever. That's always the way that video standard worked. And if you never knew that, then pat the engineers on the back, or pat the engineer in you on the back, because you never noticed it, and they were only having to send 75% of what they were really trying to show, because they couldn't encode it any faster. The standard, when they built it, couldn't handle it. The tape they couldn't decode and store enough and encode it. So you can use tricks like that once in a while. It's done less with video because we have higher expectations. And if you don't believe that, go look at a commercial that's even 10 years old, 8 years old football films, things like that on YouTube, and you're like, God, that looks like really grainy and fuzzy. But that's what we watched, and we never thought that. We thought it was fantastic. So it's kind of interesting. Our standards get adjusted. So if you're going to have to send stuff at a regular interval like this, then your bandwidth is going to determine completely how big each of these packets can be. So I, in this case, might send 24 images a second. That's what traditional motion picture movies do. This is why when you watch a really, really old movie of black and white of people walking around the sidewalk on New York, and you're watching it in the 60s or 70s or 80s or whatever, it looks like people are walking really fast. It looks like funny, like what's going on with the video? It's because they've taken 24 images a second and thrown it into a 30 image per second format. So they're only taking 24/30ths of the time to show you what should have taken 30/30ths of the time. So they're compressing time. They make it look faster. So within the image and between the image, there's spatial compression that's going on. All right, so that's a little bit more on video. You can have connections that are constant bit rate. When AT&T sends you UVerse to your house, it's a dedicated point-to-point circuit with constant bandwidth. They don't ever have to do any of this stuff. And we'll talk more about that in a little bit. You can have variable bit rate connections. Even with video conferencing services, you can have stuff like that, commercial ones where you dial up with special ISDN telephone lines and things like that, not necessarily over the internet. So this has been around a while. The telecommunications carriers used to offer a lot of services. ATM was a very popular network protocol for a while. It was kind of dominant for a while. It was layer 2. And they offered constant bit rate, variable bit rate, adjustable bit rate, best efforts bit rate, et cetera. And we ran everything in the phone network around the country on that technology. You could throw everything at it, and it would never drop a video packet. It was amazing. And I've constantly been perplexed at what happened to it? Why did it disappear so fast? So MPEG will do some of this. All right, now to get to the commercial services. When we want to stream stored video, the job is to figure out the bandwidth I've got from one moment to the next and push it out to the client. So there are protocols to help us do this. One of them runs as part of HTTP called Dash. And by Dash, what you do is divide your movie up into chunks. Well, that's kind of duh. And you will also take each chunk and encode it multiple different ways. One that uses very little bandwidth and one that uses enough bandwidth to get it sent in the highest quality you can. And what you'll do is you'll switch from one chunk compression amount on one part of a movie, and then when you move to the next chunk, if your network situation has changed, you may switch to a fatter or skinnier one. So basically think of it like this. You've got your fat one, you've got your medium one, and you've got your small one. And so my job is to send you the movie. So what I may do is send you this one. The bandwidth goes down a little bit. The next chunk I send you is this one, and it may go down further because you move to cell and you've left Wi-Fi on your phone, and then you get back into kind of a Wi-Fi, but it's a coffee shop, and then finally when you get back home again, you've got the bandwidth and you can kind of finish the movie out this way. So it also could be nothing you're doing. It could just be network congestion that's taking place. YouTube does this all the time automatically. This is why when you look at a YouTube video and you just start playing something, Siri, okay, I've got to watch this, James Veach. If you guys don't know him, he's like the nerd humorist. I've kind of really started to really like this guy. He's like everyone's alter ego. He takes the time to screw with spammers. It's just to the point where they basically write them back and say, please stop emailing us, which is amazing. Anyway, so what I wanted to bring this up to show you was a variety of bandwidths from 2160 all the way down. It's set to automatic. So if I play this for a little bit, we can see sort of where it's at. 720, so it did not pick the highest one. Did you see that? And if I open up another YouTube video and Dream Crazy, and I start playing that, and let's see what's going on here, and I start moving my mouse around a lot, I got to play it back again. And we can see it's still at 720. And I'm trying to generate a bunch of bandwidth. So it's too good because I'm on Ethernet. I made the fatal flaw of being on a reliable network this morning. What was I thinking? I could run this over my phone, which I've done before. I did it one class by accident and used up about 4 gig worth of data. That hurt. So you can see this thing kind of mess around and do stuff. One way to do it is to use Wi-Fi and walk further away and closer to your hotspot while you're watching, and then periodically click on this and catch it changing the resolutions. He's kind of hit the big time. It looks like he's gotten makeup on now, and he's got professional lighting. So I think this has become his job, which is like amazing to me that you could like turn goofing off into, I don't know why that's so amazing. I worked with a building full of people who turned goofing off into a job. All right, so you divide this thing into chunks, and what the client will do is communicate back to the server to let it know how things are going, and that's the data that helps the server make the decision on what size chunk to send, or if the client is in control, it informs the client on what size chunk to ask next. So you choose the maximum coding rate sustainable given the bandwidth you've got at the moment, and you can choose different ones as time goes by. So this is a huge help to a programmer that's trying to establish a conferencing app like FaceTime or WebEx or Skype, or maybe some sort of a YouTube conferencing or some of the Google ones that are out there. This is one. There's also one that's a layer below at the transport layer that does real-time streaming as well. That's a peer of UDP and TCP. So this one's built at the application layer, but there's other ones as well. So what CDN networks do is take the task of distributing all this stuff to users. So here's where the philosophy gets really interesting, and you see how brittle this can really become. One thing CDNs keep users from having to worry about is how are they going to send all this stuff themselves? Because what they'll do is get away from this single mega server and distribute lots of servers around the world close to where the end users are. And Akamai, for example, this one says they have 1,700 locations. How many locations does Akamai have? I have no idea if this will work or not, but I think the last time I looked, they had 250,000 servers. So it's a little bit bigger. Global locations. Let's see what they say here if I can scroll down some. These are their sales offices, I think. Yeah, it looks like it because there's phone numbers here. But I really want to see how many there are here. So I'm not going to waste too much time. There may be something back if I go back to the search in Google. Okay, yeah, right here, facts and figures. As of recently, they have, God, I should have bought stock in them. Locations, 250 billion retail, 30 terabits of data. That's why they could handle the GitHub attack. 240,000 servers, 130 countries, and they are inside of more than 1,700 networks. So that is not at all back when this was written, which was only a couple of years ago. The data was probably 3 or 4 years ago. Well, that's forever for a company like that. They had a lot less than that. So what they try to do is bring these clusters of servers, and there's various terminology that we use. So in the case if I want to watch Mad Men, what I may do is go to Netflix, find out where it is, and then they're going to send me to work with a local server or maybe one that's maybe a little further away but less busy. So I have copies that have been pre-distributed, and I'll just grab the content locally. But we've talked about that before. That's not anything new. So one term you'll hear people talk about is an overlay network or an over-the-top network or a floating network. That's to indicate that these connections between these devices don't have anything to do with the internet. They are on, in this case, Akamai's own private network that connects all of these servers into a mesh at the top, and a network that is a simpler version of what you see down at the bottom. But they're separate. They're separate. And so these vertical lines that you see from these servers that touch back to ISPs in various places on the internet is where you kind of punch through or drop in at the edge, or sometimes people will call these things with different terminology. So to show you just a little bit deeper, Bob goes to netcinema.com and asks for a video. He's given a URL. So what does your system do with the URL? It's a chicken and egg problem. Remember, you got to go to DNS, so you have to know what that URL is. Well, fortunately, we know. You have to know what that IP address is. Fortunately, we do know the IP address for DNS. We were given that when we got connected to our network this morning. But that's where we're going to go and ask, okay, I need to go to this site. What's the IP address? So I go to DNS. What DNS will do is try to resolve that locally, and if it can't do it, it'll find it in authoritative one. It'll solve that problem. But what it gets back is a different URL. It gets redirected to a different URL, in this case, kingcdn.com. So who's doing that? Who's doing that is the person who's building the DNS entries for netcinema.com. So what they make sure they do is tell you never cache this entry, because every single time you come back and ask for a movie, I may send you to a different place. Or they may let you cache it for a while, but what they're going to make sure is it expires quickly, so that if you show up and you try to go to netcinema.com, the last thing they want to do is really send you to netcinema.com for the movie, and they're going to instead send you to a place on Bob's DNS. So you get this King CDN URL, you've been redirected, and now you'll instead go to King, you go to their DNS server, and you're going to resolve this whole thing. And here's where the magic happens, because what King CDN will do is look at where you are. They'll see topographically where you are on the internet, how many hops away you are from things, where they have the movie that you're trying to watch. It may not be in all their servers, and which one is not so busy that they can handle it. So they'll have a formula that looks at a combination of those things. They'll decide which King CDN server is the one they want to send you to, and they will build a DNS record on the fly and hand it to you as if it came from the DNS database. So what you get back is something that tells you go to this box at the bottom, and then your transmission begins. So this happens every single time somebody wants to grab a movie, and it's scalable. This works well. It's not a slow process. So this is so powerful that even though it takes a bunch of round trips, it's far preferable to trying to gang up on servers that you distribute the load on just based on percent utilization. Because you may send me to San Antonio, which would be great for Microsoft Azure Data Center, or you may send me to Rio, which is not great topographically. So we will tolerate this delay up front, and allow people to prevent us from caching entries and have to go all the way back to their authoritative DNS server in order to calculate this. So how can you improve that? Give Akamai your DNS server too and let it duplicate that. Teach it the algorithms and it will calculate it nearby. They'll use this, every trick in the book they can to get this. Netflix is a little different. They don't really own a data center. They don't have a bunch of servers. So when they buy a movie, they have first Amazon build all of those different speed streams that we talked about, this one, and that one. And they'll do it in all different kinds of screen sizes because they have different ratios and different pixel counts, every type of phone and tablet and laptop and desktop and television that you've ever played a movie on. And soon, maybe theaters as well. That's not that unheard of also. So they'll build versions for each of those things. When you go and ask for the movie and log in, they will keep your credit card and password safe over here. But you'll go to the Amazon cloud where they've done all this encoding, but that's where the video is actually, the video files are all stored. So the first thing you're going to get back is a manifest file for the specific video. You'll hear this term used constantly. So the manifest file is a list of all of the sizes and bandwidths. So you have, 1024 by 768. I've got it in a 60 KB per second. I've got it in a 180. I have it in a 1 meg, a 4 megabits per second, and a 60 megabits per second. Which one do you want right now? Okay, what are you using now on iPhones? It's 8. Okay, that's like 800 by 680, and I've got that in the following ones, and on and on and on you go. Hundreds of these files. They will not encode every movie in every single one of these things because they don't expect people to watch it everywhere. So if there's a regional movie in an Indian dialect that's going to be watched in India and place where there are lots of Indian expats like Silicon Valley, and maybe New York, and maybe where there's immigrant populations at the other end of the economic spectrum in Dubai, then in those servers, they will drop versions of that movie in the various sizes that they think represent the devices and the type of connection speeds those users will have. They are really careful and scientific about it. They leave nothing to guess on this. So, and sometimes you get surprised. So like when the movie Roma, which was filmed in Mexico, was nominated for a ton of Academy Awards, what Netflix does is push it out everywhere because they know the flood is coming. So it's a very cool model and it's extremely effective. What Amazon does, they don't actually feed you the movie. They give you the manifest file, and then the movie is fed to, the last time I looked, one of 3 networks of providers, Limelight, Level 3, and Akamai, and they make them duke it out city by city. And so every few months they'll flip it over to somebody else if they think they're doing a better job. Very Walmart, very Walmart. So we can talk more about them sometime if we get a chance. So there's a totally different model out there that I ran across that was a big surprise to me because it came from the place I worked at. And I don't know, I have to be careful not to make it sound insulting, but it was just amazingly more innovative than I expected. That does sound insulting. Okay, let me just explain to you the way the thing works before I say something that I'm not trying to say and then get held responsible for it, as I should. All right, so I'm going to draw this network that we have with something like DSL. So when you buy UVerse from AT&T, they basically run a communication circuit from their central office building to your house. And in the central office building, they can use this dedicated, fairly high bandwidth pipe. It goes anywhere from 4 megabits per second to 60 and beyond. But it's never changing. It doesn't fluctuate. There's no congestion. There's no drop packets. It's a dedicated point-to-point circuit between your house and them. And increasingly, it's not even DSL. The vast majority of the time now, it's fiber to the curb, as they call it. So FTTC or fiber to the DMARC or fiber to the home. And what they use now is mostly fiber to the home. So they will run fiber all the way into your house and into the box that we're about to talk about. So this can actually go up to a gigabit per second. And the price for a connection that speed is maybe about $70 a month. When we first did the DSL trial in the United States, and Southwestern Bell did it, the commercial trial was in Austin. It was a 4 megabits per second connection, and it was about $1,200 a month. And that was the market trial we ran. It's less than, I don't know, maybe $6 a month now. The cost, they may not charge you that. So I've got this dedicated connection. One of the things I can do with it is peel off some of the bandwidth and send it to a Western Electric 5 ESS telephone switch and connect to the world's telephone network, plain old telephone service. I also can peel some of this stuff off and connect it to, the internet with a, giant Cisco router here, for example, and that's something that we're very focused on that we want to do. But the third thing that they figured out how to do with it is to plug it into this UVerse model. And UVerse is a video entertainment system. So they usually don't have this stuff in every CO like they do the other two pieces. So what they'll actually do is haul this across town to some big central area. It doesn't mean it's in downtown, but they'll have all the COs in the city all kind of coming to the same spot because they'll control everything from one big set data center worth of equipment. So what's going on here? Well, what's different about this model that makes it very innovative is they're sending one video stream at a time down this connection. And if you can watch 2 different things at once or 3 different things at once, they change it a little bit. But it's still very different than the traditional model. The traditional model for distributing video entertainment is to send all the channels you've got to everybody all the time and let them filter out all of them except the one that they want to watch. So you will have a certain amount of spectrum that you will divide up, and these will be, you're basically the channels that show up on the grid of regular networks that you've got. Then you'll have some in here for pay-per-view, where you'll reserve some channels in here to let people who want to watch things on demand, for example. And what you don't have to worry about is their playback unit, the DVR, because you build that into the local box. Right? So you can play things out that way. And then you may use some of this stuff for internet bandwidth or things like that. But it's all sent all the time. If you're using somebody like DirecTV, they may send blocks of these on different satellite frequencies. They may actually have different birds that are close to each other. So your dish may be able to receive signals from more than one satellite at a time. We call them dishes and birds, by the way. So the birds, the satellite, obviously. So that's the model that's worked. And in fact, even for the last, 75 years, 60 years, I don't really know how old cable is at this point. Even with that coax cable, the one that pokes, makes you bleed when you touch the end of it, that pokes your finger, that's that black, kind of stiffer little bit of cable, they've always poured everything they had onto that wire, and then you just had a box that filtered off everything but the one that you wanted. All right, so this one doesn't do that. This sends a single stream of IP packets at a constant bit rate and is in a specific size that never has to change, so they don't have to worry about the manifest stuff. And it sends it over this connection to your house. So here's those packets. Right? And so what happens if you decide you want to watch a show or a movie is they will start sending packets from, let's say it's stored video, it's pre-recorded, not live. They'll start sending you packets, packet 1, packet 2. They'll start at the beginning of the movie, and they'll send you the video frames in order. It's been pre-built into a file, so all they have to do is go to this file server over here and pull the data out and start pumping these packets towards you. And as long as they don't mess up their network design, it's a perfect network to do it. It's dedicated bandwidth. You don't share with anyone else. That's what dedicated means. And it's constant bit rate. So here's where it gets kind of crazy interesting. One of the things AT&T decided to do was distribute their video this way. And they looked at the stats carefully on sort of what makes this expensive to operate. And the most expensive component was this DVR, because it was a hard drive for years and years. And they broke all the time. So every time they break, you have to send somebody out to the house to work on it, and that's called a truck roll. You're going to send a truck out there. Truck rolls for AT&T are about $150 a piece. So if you can get rid of a couple of million truck rolls a year by getting rid of the DVR, because that's the most frequent thing to break, and you don't just ever need to go out there and visit otherwise, you've saved the company hundreds of millions of dollars. So immediately you have an advantage over your competitors. You're going to have to invest in some equipment because this means there's no DVR. You may have a tiny little cache to buffer a second or two, but no DVR means if you decide you want to go back and play something, I'm going to have to have stored that on my storage systems, which are enterprise grade and don't fail like that and have failover and backup and everything else, and start sending those clips to you. So what happens if you hit pause on your remote control? Well, your little cable box here for UVerse sends an IP command back to this head end, and maybe it would be a little better if I change colors, might make it a little easier. So you hit the pause button on your remote control, and it sends a command message back over here. And what it does is it pauses your video. Now, if pausing your video means it stops sending packets, your TV is going to go blank because your TV is expecting a signal every second. So let's talk about what pause really means. Even on a traditional cable box at your house, when you hit the pause button, it just continues to send data, it continues to send video at exactly the same rate it did before to your television. If it's via HDMI, it's digital. If it's via a baseband RS-170A cable, then it's just with a frame, basically analog signal. But it continues to send it at the same rate. It's just sending the same picture over and over and over. And with pause, we expect them to mute the audio as well, instead of going or whatever the little sound was and repeating it over and over. So what AT&T has to do in the UVerse example, or anybody else who builds an architecture like this, is they have to grab whatever frame you are on and just start sending that at exactly the same number of bits per second, the same number of packets per second, over the same single IP connection. And it gets down here, and nobody knows what's going on except you. You can see visually what's happening, but the box hasn't done anything different. Your TV and network haven't done anything different. So that's kind of interesting because the pause now is a different data stream that the provider has to send. All right, that makes sense. So far so good. What happens if you hit fast forward and you want to kind of skip forward at double the normal frame rate? Well, you can't tell your hard drive to start spinning twice as fast. And you can't sort of skip over packets. That's a problem. So it turns out the only thing you can do is build a separate file. So instead of building a manifest's worth of files with different compression formats, what you're going to do is build files with different sequences of the same movie. So in this file, which I'm going to call the fast forward times 1 file, this is video frame 1, 3, 5, 7, 9, 11. You skip every other one. You can make it the even ones. It doesn't make any difference. But you're going to send the same number of packets per second, the same bits per second, over the same connection to the same box. Nobody will know what's going on different. But if you hit fast forward here, then it's going to switch you to the other file here, right? So there has to be a mapping that shows that these two are related and that this one is related to here. So if that's when you hit fast forward, we know to skip down there, and we continue playing the movie until you hit play again. And if you hit play here, then I'm going to send you to that part of the file again. So the same thing happens if you hit other forms of play on here, like fast forward times 2. It's going to have 1, 5, 9, 13, 17, 21, and so forth, 25, etc. And you'll play that file, same number of frames per second. It just looks like it's going 4 times as fast. And on these, you don't mute the audio. Usually people, they want to kind of hear the audio, so you can kind of catch maybe an audio cue as well, like a band or sound or something like that. So really interesting way to do it. How are you going to do rewind? Somebody hits pause and then they start backing up in the movie. How are you going to do that? Well, the way you end up having to do that is by putting the file in backwards. So the first packet in the file is the last frame of the movie, and then the next packet in the file is the next to the last frame of the movie, and so forth. So if you're here and you hit backup, then you're going to be set to this spot in this file. So I'm moving around between these files in my manifest, and that's how I'm basically giving the illusion. If you change channels in the middle, then it starts sending a different video stream. And there's a noticeable lag. It's maybe 50, 100, 200 milliseconds, but you notice it. It's not instantaneous, but you acclimate to it very, very quickly. So it's not bothersome except the first few times it does it. And you can switch to anything they've got. So they can have an infinite library, many, many more selections to send you than what a traditional cable network would have, because they're not limited by being forced to send only as many different signals as they have bandwidth. Maybe they have enough to send you 100 things, but what if they wanted to send you 200 things? Well, they can't do it. Well, this one can, because all it ever has to send you is one thing. For live sports, you encode it on the fly. When people start watching it, you start making copies of the packets so they can go backwards to the beginning of where they watched. You can make optimizations by sending things to people all at the same time. You license videos from Hollywood. I mean, they had to become kind of a Hollywood studio in a way. They had to sign agreements with Disney, and so we had some Hollywood guys running around the phone company with sunglasses and buildings, and we were joking about it, but it was kind of crazy. You also had to hire people that watch videos. One of the things that some of these cable providers want to do is allow you to rent videos that are not suitable for public display. Pornographic movies or quasi-pornographic movies. There's also rules in various countries about the kinds of movies you can show. There's censorship. Some of it's religious or politically based. So for people who want to upload things into this archive, we gave people a way to kind of submit movies to be made available for pay-per-view. And so you had to hire people to watch these things. And the contracts that we had to get them to sign, because if I pulled up the wrong site at work, I'd get a phone call. I mean, you'd get in trouble for doing it. They actually tracked. And it was really a pain in the butt because I had a lot of customers, and one of them was Office Depot, and I could never bring up Office Depot's webpage at work to kind of do research and read their earnings reports and things, because too many people logged on and used their corporate credit card to buy office supplies instead of through the negotiated supplier, which was, I think, like Aztec Office Supplies or something. I'm like, God, give me a break. So you had to hire people, and you had to have them sign contracts that they wouldn't sue you for being exposed to offensive material at work, and they wouldn't consider it sexual harassment, and just all kinds of crazy stuff. So probably for a bunch of reasons, but maybe for some of those as well, they've backed away from this service, and they bought DirecTV, and they're trying to push everybody over to that side, or at least let them run that whole network. So a very, very different application for doing this. There's still tons of innovation left in this marketplace. I talked about some other things in yesterday's video that were happening, but all of this stuff like picture-in-picture and channel surfing and showing you a grid of all the movies and stuff, all that stuff is built in software, encoded in real time. So if you're seeing a movie, if you're watching a grid that's showing you like this thing of the list of shows that are coming up in a timeline over here, and then thumbnails that are in full motion of, like what's the baseball game doing, what inning are they in, so little thumbnails of these, all that stuff has to get built by people looking at these files, including the live ones which are being built in real time, and reducing it, dropping it on here, putting the things together, pulling the database together for the grid, and then building a single frame, one single frame of this video, and sending it down the line, and then doing it again for the next one and the next one. So there's some really good coding that happens in these environments, some really complicated, interesting systems that get built. So video's got just fascinating opportunities. I remember looking at some of the jobs that that Major League Baseball had for some of their motion services, and there was some really cool work out there. And much earlier in my career, I considered going in that direction. Okay, so we need to wrap up by talking about making sure we get to sockets again. You've taken a look at them already. There's not going to be a socket assignment in this week's homework. I'm going to give you guys a break after apparently almost killing everyone. And I guess that's, first of all, let it be a lesson to not wait until Sunday to start it. I'm not going to do extensions anymore without penalties. So if you have a special circumstance or something, my advice is start early on the homeworks because it's becoming epidemic. So I'm kind of doing this for all 9 classes, and the department is putting pressure on in both universities to like knock it off and stop coming up with quite so many extensions. So I'll keep them with mild penalties and give you guys chances for extra credit. So if you do have something that's unavoidable, it's not going to flunk you. It's not going to kill you. But your best bet is to start early on things, okay? Because I don't consider that an overwhelming homework. And if you talk to people that took this class in the summer, they had one of those every other day, just exactly like that. The class was a month long, so we did like 15, and they came to class for 2 hours in the morning and spent the rest of the day on the homework. Sorry. So sockets are the software interfaces they're like doors between what you're sending that you want to have get on the network and the software that runs as part of the operating system as root beneath you. There are 2 popular socket types. There are not just 2 socket types, so that's incorrect. There are 2 dominant ones, UDP and TCP. So the way these things work is you will read some data from a user. Let's say I wrote a program to ask somebody to type in a sentence for me. All right, I will build a message out of that, and I'm going to send it off to a server. Doesn't have anything at all whatsoever to do with a web server. It's just any generic type of server, in which I'm running a program that's waiting for these lines of text to come in. And what this server does is very simple. It converts what I've given it to uppercase and sends it back. Okay, so the server will send the modified data back. The client will receive it. It will push it all the way back up to the application where my program receives it and then displays it for the user. Very doable lab assignment. Very doable to write the client and server parts of this and to run them. You can run them on the same machine, after all. We just saw doing that with Mailcatcher, remember? So with UDP, it's one that is a bare bones transport protocol. I like to call it the evil twin brother of TCP, the lazy evil twin do nothing brother of TCP, because it basically doesn't do anything. It doesn't try to ask permission of the other server. It doesn't look to see if the server is turned on, if it even exists or not. It doesn't do what we call handshaking. So the other side's not expecting us. And when I send it a packet, it's out of the clear blue sky. It's a one-off, one-time packet. The very next one that I send has to have all the same information in it about what destination am I trying to reach. So for me, it's bad sometimes if I want this concept of a conversation, because it basically means every single time I say a sentence, I have to start by saying the name of the person it's from and the name of the person that it's going to. With every single sentence, really? Well, just think if you write a book and you decide to mail it to someone, but you only have stamps for regular envelopes. So you're going to have to send a few pages at a time, a message at a time. And on every one of those messages, you're going to have to put the sender address and the receiver address, etc. That's the way UDP works. It doesn't also worry about overwhelming the network or overwhelming the recipient. It will send those 10,000 pounds of sugar without bothering to find out if you're ready for it or not. It will send whatever you ask it, and as often as you ask it. So for that reason, lots of network managers will filter out all incoming UDP traffic unless it's in response to a connection that somebody inside the organization initiated with someone. Like they opened a UDP connection to get streaming radio, for example. So some places really worry about this because if they want to send something over UDP like Google does with HTTP2, then they have to deal with the fact that some of these network managers will never let it in. So it turned out that things were better than they thought, but that's kind of a reaction that we've seen to UDP. It can be used to overwhelm users. It can be used for attacks. It can be used for denial of service. So lots of managers just don't let it in unless it's in response to a specific request. So for the app, it's an unreliable data transport model, unreliable data protocol, UDP. And anything you want as far as reliability, you're going to have to do yourself. So let's look at how UDP would work. Like in all protocols, the server needs to be up and running first. McDonald's opens their doors. They have employees there. They don't really know that they're going to have customers today, but they certainly don't wait until there's one there before they decide to open the restaurant and turn on the stoves and get the food ready, right? So they don't wait. They start off the morning getting ready and waiting for a client to come in. So they will open a socket call. SOCDgram is the specific term that indicates it's a UDP connection. SOCStream is the variable name that you send if you want a TCP connection, which we'll come to next. And so you create the socket, and you're given back a data structure or a pointer, basically, that you store in this variable. And you enter a read mode from the server socket with a command. And on the client side, they've started up a program. They've handed a message, a lowercase sentence, down to the transport layer where UDP will build a socket, and they will connect to another IP address over the network at a certain port number, and they will use this socket command to deliver the data. The read command finally terminates because it's been waiting for a read to complete. It looks like the world's slowest protocol maybe, but the world's slowest subroutine, but that's because it's waiting on something to happen. So it finally gets the data, it makes the change, it will write the reply to the destination back again. It will use the data that showed up to create the return address and send it back to the user. So that's kind of the way UDP is going to work. So if we kind of step through it, your Python code that you might write is from socket, you're going to import, you're going to set your host name up for your server you're trying to get to, you will specify the port number you're trying to get to, you will create a structure and initiate the socket with this command. It will return something you store in this type of variable. This indicates that it's UDP. Then you can define a message by using raw input. It will convert it into the right format, and then you call client socket send to with that message. You will ask it to be encoded, so there's a period between these two. It's kind of a subpart of it. And then you must include the server name and server port in every single packet you send, because there's no conversation going on. It's like a one-off. It's just an envelope in the mail. And then the server will modify the message and send it back to you. So you wait on that, what they receive from. You tell it how many bytes you're willing to receive. When the server gives it back to you, now you have it. You basically have the address where you've stored that, and you will print out that modified message and then close the socket. All right, so I'll skip through a bunch of these slides because we just talked about it. On the server side, they're basically doing the same thing. They don't need to know their own IP address. They just decide what port number they're going to bind to their program. So they will create a socket, and they will bind their code to that socket. So they're the only one that is going to be sent data that arrives on port 12,000. They may print out something for you, and then while true, which means forever, you stay in this loop where you're waiting to receive a message from the user. You will modify it by passing it up to the next layer where your server code is going to convert it to uppercase, presumably, and then give it back to you. And you will then send that modified message, so you know that's done. When this completes, it puts the result here. Then you send that result back to the user by encoding it into your packet and send it back to the address. All right, so TCP is different. TCP adds a lot of reliability. It handshakes with the other side and establishes an ongoing communication. So it creates state. So one thing you don't have to do is put the addresses on anymore. So what they basically do is set a box on your desk and say, whatever you put here will magically show up in Bob's mailbox on his desk tomorrow. So it's sort of a dedicated mailbox. And whatever you put there, you don't need to put the address. You just have to order the box, and it comes and they install it on your desk. And that's the connection. You've asked permission to do it, and Bob's agreed, and so you guys both do this. And now anything you put in that tray, someone's going to pick up in the afternoon and deliver it over to Bob the next morning. So that's kind of the analogy about how TCP's handshake is different. So the client has an extra job to do at the beginning of this process. It has to ask permission. We saw that when we looked at UDP this TCP connection earlier, and we saw this SYN, SYNAC, and ACK. That's the handshake, and we'll learn more about TCP details, but that's what's going on here. And then from then on, it's pretty much the same, except you don't have to send the packet every time. We use SOC stream instead, and you will encode your sentence and you send it off. But you'll notice one of the things that you don't bother putting in this is the IP address of the host again, because you're now sending it as part of a ongoing connection. All right, and then the server basically has code that will bind to things. It's ready to listen. Whenever it gets a connection, it will now create a socket specifically for that incoming user, because it's now dedicated. So every user that connects to the server is going to have a different socket that keeps their data separate, but allows me, so different trays on my desk, if you will. So I'll use that to send things, you know, back and forth. And there's a little bit more in here that they walk through, but we've talked about it. So that's it. We made it through chapter 2. We've kind of went fast, but there's a ton of stuff in there. We learned about sockets a little bit today, quite a bit about streaming and CDNs, and about a bunch of protocols, if you can remember back to the beginning of chapter 2 a couple of weeks ago. So we've covered a bunch of stuff in here. Messages are either sent in or out of band. We didn't really talk a whole lot about it, but an example of an in-band control message would be that dash protocol sending messages back along with the video that's coming back and forth to say, here's how it's going, you need to slow down or speed up or whatever you might do. Out-of-band signaling includes things like you type in an address on your telephone by typing in someone's phone number. It's really an address. The equipment sends messages around to get things set up. It does not travel over the same connection that the voice call is going to travel. And so that is considered out of band. It is not part of the same communication stream that the intended data transfer is. Centralized, decentralized with like DNS, stateless versus stateful, like with HTTP and TCP versus UDP, unreliable versus reliable. We talked about headers or fields in front of data. So we've made it through, guys. Pat yourselves on the back, and we did it on time. So that's what I have to cover for you guys today. I'm going to take a quick peek at chat. And why isn't that Peter Jackson fixing his world worn? Yeah, I do want to watch. There's one out there on the Germans' perspective of D-Day that I'm interested in listening to as well. Can we talk about the ducks? The ducks. You lost me on that one. We have a ton of ducks on campus. Have I talked about those ducks? Oh, yes, thank you. Got it. Yeah. All right. Thank you, guys. Have a great weekend. I'll see you back in class in person on Tuesday. But, oh, yes, I watched that whole video. Oh, my God, that was crazy. He's insane. All right. See you guys. Bye. Now I know what you're talking about, the ducks. Just one duck, please? A giant duck. All right, see you.